Okay, let's unpack this. Imagine a scientific belief, one that's stood solid for like 100 years, a real cornerstone for how we thought light and matter work together.
Right, a fundamental principle.
Exactly. And now, picture it being seriously challenged, maybe even overturned by a brand new discovery.
Yeah.
That's what we're diving into today, well, potentially revolutionary shift in photochemistry. Welcome to the deep dive. This is where we sift through the latest research, cut through the noise, and pull out the key insights for you. Think of us as your guides through the sometimes dense source material.
Definitely. And today our main source is this really intriguing study. It just came out, published July 16th, 2025 in the Journal of the American Chemical Society.
Okay.
And it got picked up by SciTech Daily today, August 18th. So our mission here, our deep dive, is to figure out how a molecule's immediate surroundings, its microenvironment, can drastically change its chemical reactions.
Way beyond just how much light it absorbs.
Precisely. And we want to explore why that's such a big deal, potentially, for you.
So traditionally, the thinking in photochemistry was pretty straightforward, wasn't it?
Yeah, very much so.
The color of light a molecule soaks up the most, that should be the best color for making it react. Makes sense on the surface, more light in, more reaction out.
Seems logical. But what's so fascinating now is this global team led by researchers out of Queensland University of Technology, QUT.
Ah, QUT.
Okay, they've found this hidden factor, this mechanism that sort of reframes that whole century-old idea. They're saying the local environment around the molecule plays this critical, really crucial role that we've mostly overlooked.
Okay, wait. This is where it gets really interesting then, because it bumps right up against that basic assumption, doesn't it?
It really does.
Dr. Joshua Carroll, he's one of the lead authors from QUT's Soft Matter Materials group. He actually said, and I'm quoting, "Our experiments confirm that the microenvironment around each individual absorbing molecule can lead to vastly different properties." So it's not just the light hitting it, it's what's literally next to the molecule that changes the game.
Exactly. It's the neighborhood effect, you could say. And they've actually linked this behavior to something already known in fluorescence science. It's called the red edge effect.
The red edge effect. Okay, what does that mean in simple terms?
Well, basically it means sometimes hitting a molecule with slightly lower energy light that's shifted towards the red end of the spectrum.
Even if it doesn't absorb that light best.
Right, even then, that lower energy light can actually make the molecule more reactive. It sounds weird, but it's because this gentler nudge lets the molecule hang out in its excited state for a bit longer.
Oh, okay. So it stays energized longer.
Exactly. It has a longer excited state lifetime. More time hanging around in that energized state means more opportunity to actually do chemistry before it just fizzles out and loses the energy.
So it's not just about the amount of energy absorbed, but the duration it holds on to it, giving it that window to react.
You got it. And that's the key insight. It opens up possibilities for reactions using light we previously thought was, inefficient or just wouldn't work well. We're not just limited by the absorption peak anymore.
That really is a fundamental shift. So it's not just throwing any light, but the right light in the right place, giving it that crucial extra moment.
Precisely. And they didn't just theorize about this. They backed it up with some pretty sophisticated experiments.
Like what? What did they do?
Well, they used fluorescence spectroscopy. Think of it like listening to how a molecule handles energy. You shine one color light on it, see what light it emits back. That tells you a lot about its excited states.
Okay.
And they also use something called photochemical action plots. These are great because they map out exactly how effective different wavelengths, different colors of light are at actually driving a specific chemical reaction.
So they could pinpoint which light worked best under which conditions.
Yes, and show that it wasn't always the light absorbed most strongly. They believe these techniques together provide really solid proof for this microenvironment effect.
Right. So connecting this to the bigger picture, the principal investigator, distinguished professor Christopher Barner Kowalik, he called the potential impact enormous.
That's the word he used.
This idea of controlling reactions just by tweaking the surroundings.
Yeah.
It almost sounds like science fiction. What kind of radical new things could this enable? Maybe in medicine, for example. Stuff that wasn't even conceivable before.
Well, yeah, it's more than just, a scientific curiosity. It's like finding a new control dial for chemistry that we didn't know existed. Imagine tuning a molecule to react strongly to a certain light. Even if it normally doesn't absorb that light very well, just by changing the solvent it's in or designing molecules nearby to help out, Think about what that could mean. Maybe super efficient solar cells that capture light better. Or, in medicine, photodynamic therapy, where drugs are activated by light. But maybe now you could use less intense light or more deeply penetrating light, making it safer and more targeted.
That would be huge for targeted therapies.
Absolutely. Or think about 3D printing maybe achieving much finer detail or using materials you couldn't use before just by controlling this light-environment interaction. It really could transform fields like, advanced manufacturing, healthcare, drug delivery, polymer engineering, creating materials with very specific properties.
Just by managing the neighborhood and the light.
Just by managing the neighborhood and the light, it gives chemists this whole new toolkit.
Okay, so boiling it all down, the core takeaway from this deep dive is we're shifting, right? We're moving away from seeing light absorption as the be-all and end-all for photoreactions.
Correct. We now understand, or are beginning to understand, the really deep, profound influence of the molecule's immediate surroundings, its microenvironment.
That is a profound shift. And it really makes you wonder, doesn't it? If a molecule's unseen local environment can fundamentally change how it reacts, what other microenvironments are out there in life, in science, maybe even in our daily lives, shaping things in ways we're only just starting to grasp?
That's a great question to ponder. What unseen contexts are influencing outcomes everywhere? It's definitely food for thought.